Today we are going to discuss problems of general principles and process of extraction of metals of NCERT book. This is the 6th chapter of 12th standard and we are going to discuss problems one by one. The other name of this chapter is Metallurgy simply. You study this chapter in name of Metallurgy. We are going to discuss problems one by one in next 2 or 3 class of this chapter. The first portion that is asked is copper can be extracted by hydrometallurgy but not zinc. We have to explain it. The first question, that is 6.1, is asking about copper can be extracted by hydrometallurgy. But zinc cannot. How can we explain this one? We have to explain this phenomena, this process. How we can explain this process? Copper can be extracted but zinc cannot. If you know the process of hydrometallurgy, you must be knowing that hydrometallurgy is a process in which powdered ore is first dissolved in a suitable solvent, and then after dissolving in a suitable solvent, a strong reducing agent is kept there to reduce metal ion into metal. Copper is a less reactive metal, less electropositive metal, and it can be easily displaced from its salt by a more reactive metal like zinc. But as far as zinc is concerned, it is a highly reactive metal and it cannot be displaced from its salt to form zinc. However, if you take more reactive metals like sodium, potassium, etc., which can actually reduce zinc, but these metals are so reactive that they will react with water to form H2 gas. They will not displace zinc, but they will displace hydrogen H plus from water and form H2. And that's why zinc cannot be used in hydrometallurgy. The process that the method I am telling, I am writing down here. Hydrometallurgy is a process in which powdered ore is first dissolved in a suitable solvent, and then more electropositive metal displace metal cation from its salt. For copper 2 plus, it is a less reactive metal, less electropositive metal, which can be easily displaced. Copper 2 plus salt is dissolved and you can use zinc, a more electropositive metal, and copper will be displaced from its salt. This is the phenomenon. However, for zinc 2 plus, which is a more reactive metal, zinc 2 plus cannot be reduced by higher electropositive metal. We have to take higher electropositive metal than zinc, like sodium, potassium, rubidium, etc. These are highly electropositive metal. But if you take these metals, sodium, potassium, rubidium, but sodium, potassium, rubidium are so reactive that it will react with water to form hydroxide and H2, and they are not going to reduce zinc at all. So you are saying that the problem that with zinc is a highly electropositive metal. Other metal cannot reduce it. Even if you take a more electropositive metal than zinc, there will be reaction with water of these metals, and water from water H2 will be produced, and that's why zinc cannot be used. Zinc cannot be extracted by hydrometallurgy process. So this is the explanation here that you can easily understand. The next question is, what is the role of depressant in fourth fluorination process? 6.2 is, what is the role of depressant? Fourth fluorination process is a method of concentration of ore of sulfide type. Sulfide ore can be concentrated by fourth fluorination process. If we have to concentrate a mixture of sulfide ore, then we add different materials which are called depressant, activator, and other are collectors also. These additional three materials which have different use in fourth fluorination process. So first of all, fourth fluorination process is a concentration method of sulfide ore. If we use mixture of sulfide ore, or there is in ore more than one sulfides are present, sulfide ore, then we have to use depressant, activator, etc. other than collector also. Collectors also. I am writing down the use of these three. Actually in this question only depressant has been asked, but I am writing down the process of use of these three in fluorination process here. Consider, for example, ZNS plus PBS extraction. ZNS and PBS extraction, if you consider, we have ZNS plus PBS. It is reacted with, first of all, it is reacted with, suppose you are taking NaCN. NaCN will dissolve ZNS and form Na2ZnCN whole 4 and then Na2S. This is the process. So it is depressing. It is actually dissolving ZNS into ionic compound, and that's why it is more dissolved in water. So this is called depressant. Actually depressant depress one of the sulfide ore to move into the fluid. If you are knowing fluid fluorination process, you must be knowing that the material which is water repellent, that is less polar, that is more covalent character, will move into fluid. So these compounds having a significant covalent character, and they will move into fluid. If we don't depress one of the material here, then both will simultaneously move into fluid, and then after we have to separate them, which is a difficult process. So we do that. We use depressant, and depressant depress one of the material to move into the fluid. Depressant form ionic complex with ZNS, and hence remain in water, which becomes water soluble and remain in water, and depress it to move into fluid. Now if you proceed for fluorination process, then PBS can be extracted. Now PBS can be extracted. PBS can be concentrated, I can say concentration. After concentration of PBS, we add activators. We add activators which activate the depressed material, depressed ore back into froth by formation of obviously more covalent compounds. So if you took Na2ZnCN whole 4, and if you take the suppose you are taking K2SO4 etc., so it will be going to form NaCN plus KCN plus ZnSO4. So this is the material which will move into froth, and you will have zinc sulfide moves into the froth. This is called activator. So activator actually activate the depressed material to move into the froth. There is other material I have written here, collectors. Collectors, as I have already told, that material will move into froth which has significant covalent character. If you look at the ZnS and PBS, these are seems to be ionic compound. There are significant ionic character in these molecules. So how we will make it more covalent, make it water repellent? We use collectors here. Collector do what? Collector do, if we have Zn and sulfide, delta minus, delta plus, collector attach themselves with delta plus and delta minus and make it non-polar. Make it non-polar. After attaching with collector, it becomes non-polar and hence it can easily move into froth. The next question that is asked is 6.3, and 6.3 is, why is the extraction of copper from pyrite becomes difficult than it's from oxide or through reduction? It is asked that from Cu to S, copper extraction is difficult. From Cu to S, copper extraction is difficult, and from copper oxide ore, it is very easy. It is told that copper oxide ore can be easily from CUS, copper can be copper extraction is difficult, and from CuO, copper extraction is easy. How we can explain it? If you look at the reduction process of this one, suppose with carbon, you will have Cu plus CS2, which has a more del G value. Del G is more positive. I am not telling this is positive value, but I am telling that it has relatively more positive value. If you took CuO with carbon, 2Cu plus CO2, then del G here will have, del G is more negative. And if del G is more negative, the process becomes easier. So del G is negative, del G negative make the process more spontaneous. Since del G negative means spontaneous process and del G positive means non-spontaneous process. You can see these problems in this way. The next question is 6.4, and which is asking about, we have to write about zone refining and column chromatography. Zone refining, first of all, I am writing. Zone refining is a method used to purify semi-metals like germanium, silicon, gallium, etc. In this method, actually this method is based on the principle that impurities are dissolved more in liquid phase, molten phase than in solid phase. And in this process, we apply heater on the metallic rod, impure metallic rod, and the heater should be movable. As we move slowly the heater, it will melt the portion of the impure metal in which impurities get dissolved. And as it is passed by, it will dissolve the impurities present at that portion of the rod. In this way, you will see that after completing this process with molten metal, some impurities will be extracted out. If this process is repeated more and more times, you will get ultra pure metal by this method. So, this method is used for semi-metals like germanium, gallium, silicon, etc. In this method is based on the principle that impurities are dissolved more in molten metal. In this process, a movable heater is applied to metallic rod. A movable heater is applied to metallic rod, and as heater move, impurities are moved with molten metal. This process is repeated many times, and you have ultra pure metal obtained. If you look at the process, I am just starting with, this is a metallic rod and I am applying heater. This is the circular spherical heater and it has to be moved. As it moves, suppose if it is present here, it will melt this portion, and as it moves, it has molten part here, This is the black part is molten part, and in this part, as we move here, this molten part will also move slowly, and with this molten part, all impurities of nearby metals will get dissolved. As it moves further, it will dissolve impurities of all metals, and in this way metallic rod will become pure. If this process is repeated more and more times, the ultra pure metal can be obtained by this method. The next point we have to explain is column chromatography. We have to explain column chromatography. Column chromatography can be used to purify that type of metal which is present in very less amount, or the impurities and metals are of similar reactivity. This method is used to purify metals of very low concentration and metals of similar reactivity with impurities. Metals of similar reactivity with impurities. This is called column chromatography. In this method, actually we do what? In this method, there are two phases used. There are two phases used. First is a stationary phase, which is nothing but Al2O3 solid kept in a column, and second one is mobile phase, which is a liquid or gas phase, moves through a stationary phase. We have to move these phase through stationary phase. The principle behind this method is different substance get adsorbed to different extent in an adsorbent. As mobile phase moves through stationary phase, the less adsorbed material moves faster and adsorbed material moves slowly. The adsorbed material can be easily extracted from the stationary phase by using a suitable solvent called element. The adsorbed material can be easily removed by using a suitable solvent called element. So this is the process of column chromatography. Actually, in question number 10, we have been asked about, I am just discussing 6.10 because it is about chromatography. I am discussing simultaneously these two questions. This is 6.42, but I am discussing 6.10 also because these two questions are actually similar. Here we have to explain about chromatography. Chromatography means chromo means color and graphene means write. So chromatography is a method in which color of different matters matter in the process. Actually, there are different types of chromatography. Different types are gas chromatography, paper chromatography and column chromatography. The principle behind chromatography, any type of chromatography, is this one. The principle behind chromatography is different substance get adsorbed to different extent in a particular adsorbent. This is the principle behind all types of chromatography, no matter you are doing gas chromatography or paper chromatography or column chromatography. The principle behind all these are that different substance get adsorbed to different extent in a particular adsorbent. So the term chromatography comes from chromo and graphene, that means color right. So this is the question number 6.10 that I have discussed with this question itself. The next question is 6.5. And 6.5 is out of carbon and CO, which is beta reducing agent at 673 Kelvin. If you look at the process here, carbon will oxidize to CO2 and CO will oxidize to CO2. Here it is del G1 and here it is del G2. At 673 Kelvin, del G2 is less than del G1. Hence, oxidation of CO is easier, and that's why CO is beta reducing agent than carbon at this temperature. If a species is getting oxidized more easily, then it will reduce other materials more easily, and that's why it is beta reducing agent. The next question is 6.6, and this question we have to ask, name the common elements present in the anode mud in electrorefining of copper. Why are so they present? When you do electrorefining of anode mud, a mud-like material is deposited near anode in electrorefining of copper or any other metal electrorefining. The metals or element, you can say metals that are present in anode mud, we have been asked about this one. Anode mud are gold, platinum, silver, selenium, trillium, antimony, etc. These metals are present in anode mud because they are very less reactive. These metals are very less reactive, and hence they are present in anode mud. They are anode mud. They will not react with any other species present in the solution, and hence they are present in anode mud. The next question is 6.7, and in 6.7 it is asked that write down the reaction taking place in different zone of a blast furnace during extraction of iron. Actually, if we take blast furnace simply here, you will have 4 zones here. Zone 1, Zone 2, Zone 3 and Zone 4. This is charge is partial charge, means ore plus reducing agent or plus flux. This is added here. Zone 1 has temperature of 1500 degrees Celsius to 1600 degrees Celsius, 1800 degrees Celsius. It has zone 2 has temperature of 1200 to 1500 degrees Celsius. Zone 3 has temperature of 700 degrees Celsius to 1000 degrees Celsius, and zone 4 has temperature of 400 degrees Celsius to 700 degrees Celsius, 800 degrees Celsius. So this is a different zone, and the reaction at different zones are, zone 1 actually is called zone of combustion. Here the reducing agent carbon will react with O2 to form CO2, and with react with to form CO. Both are exothermic. Both are exothermic reaction, and hence high temperature is maintained. Both are exothermic reaction, and hence high temperature is maintained. Zone 2 is zone of fusion, where metal is getting metal in fused state and slag formation. Here metals, first of all, iron solid, which is formed in zone 4, will convert into iron liquid, and then other portion is, if you have CaO like impurities, it will form CaSiO3. Slag will be upper, slag is lighter, so this is upper, and this is metal here, iron here. This is called pig iron, as extracted from blast furnace. This is here slag metal, molten metal is present here, slag is present upper side for this metal. Zone 2 is this one. Zone 3 is zone of adsorption. Zone of adsorption, where you will see that carbon monoxide react with this one to form CO2. Carbon monoxide will react with oxygen to form CO2, and this is an endothermic process, and that's why I think this is the node of the process, CO to react with carbon to form CO. This is endothermic process, and hence temperature decreases. And in zone 4, zone of reduction, here actually iron oxide is reduced into Fe3O4. Fe2O3 first reduces by CO into Fe3O4 plus CO2. Again Fe3O4 is then reduced to CO by FeO plus CO2, and then FeO is again reduced by CO to form Fe plus CO2. This iron that is formed here will move downward and get molten at zone 2, and it can be extracted from the bottom of the tank, bottom of the chamber. This is the different zone reaction in extraction of iron. The next question is 6.8, and 6.8 is, we have to write extraction of zinc from ZNS. Process of extraction of zinc from ZNS. ZNS is first concentrated by froth production process, and then second step is roasting, in which ZNS convert into ZNO plus SO2, and then we have to use carbon reduction process, or you can also use electrolytic reduction process. Carbon reduction process can be also used here. Now ZNO can be easily reduced by carbon to form zinc plus CO2. So this is the process of extraction of zinc from ZNS. The next question is 6.9. and we have to take use. The question is, what is the role of silica in extraction of in metallurgy of copper? Use of silica in copper extraction. Generally, copper is extracted from CuFeS2, and if we use oxygen here, then you will have Cus plus Fes plus SO2. First is formed here. Now Cus is reacted with oxygen to form CuO plus Cus. Means partial oxidation only occur. And CuO will get formed. And if we use Fes with oxygen, we will have again, it is going to convert into FeO. Now FeO has to be removed by slag formation, and that's why SiO2 is added. Actually, Fes present in the copper ore will be converted into oxide by oxidation. Actually, copper is partially oxidized, but iron is easily oxidized because plus SO2, I can say plus SO2 here. Actually, I have to write first it as CuFeS2 convert into CuFeS2, actually Cus plus Fes mixture, and if oxidation is done, then partial oxidation of only copper sulfide occur, but complete oxidation of iron sulfide will occur into iron oxide, and the iron oxide has to be removed by slag formation with SiO2, and that's why we have added SiO2 in the copper extraction. So these are some problems that I have discussed here in this class. In next class we will go into solve some more problems of this chapter.